Hey, let's turn our attention to the sideboard real quick here, okay? So on Fun Sock Friday, we got that treater there. We have SWBA. What's SWBA stand for, guys? Reese? Students will be able to. I say the T is silent. That's a joke, okay? Does anybody get that joke? I don't think so. It's funny. I think it's funny. Anyway, so it's like, okay, if a letter is silent, do you still write it? Like in gnat. What letter is silent in the word gnat? G, right? Okay, but you still write the G when you spell it out, right? Or like pterodactyl, what letter is silent?
P.
P, right? Really? Like you don't pronounce it pterodactyl, okay? Hey Justin, would you be willing to get the door for me? Thanks, buddy. Okay, you don't call it pterodactyl, you call it a pterodactyl, but you still write the P there. Well, if it's SWBA, but if the T's silent, you'd still write it, wouldn't you? I just think it's funny to say it. Anyway, so classify numbers using the number system. We're going to learn to classify numbers using the number system, okay? You guys have, I believe, done that in 8th grade as well, especially if you're in Plasmid. But we're going to, this is all a kind of a review chapter anyway, okay? And so that's section 1.6 here, and then, look here, test in 2 Mondays, okay? We don't have school next Monday. We have a 3-day weekend, whoop, whoop, okay? We have Labor Day. And then Friday, we don't have school either. We have no classes, okay? Because of the Harvest Festival, okay? So on Friday, we don't have classes because of the Harvest Festival, parade, all that stuff going on down there. We actually don't even have classes next Friday. So we only have a 3-day week, meaning I only see you guys next Wednesday, my dudes, okay? I only see you guys next Wednesday. So on Wednesday next week, we're going to be working on this review for the test, and then we'll be testing that following Monday. Heads up on that, okay? I'll talk more about that later. Just kind of to get your head in the right mindset. Hey, that's going to be coming. Yes, Seth?
Your flag.
Yes. My flag is waving. Isn't that patriotic?
No. Very.
You know, the way the air goes through the hallway, it doesn't close the door all the way. And it's kind of weird. Square root. Square root. We're going to first talk about this idea of a square root. It's one of 2 identical factors of a number. One of 2 identical factors of a number. Okay? So it's any number, you can have 2 numbers that multiply to get it. Okay? You have 2 numbers that multiply to get it. Those are factors of the number. Now, if it's the square root, that means it's 2 of the same number multiplying to get it. It's like 3 times 3 is 9. So we'd say the square root of 9 is 3. The square root of 9 is 3 because it's identical. It's the same thing. 3 times itself is that. A perfect square is a number like 64 with a square root that is a whole number. Okay? A perfect square is a number like 64 with a square root that is a whole number. It doesn't happen for every number, okay? And actually, before you flip, you're going to write some more stuff on the bottom of this page, heads up. Before you flip, we're going to write a little bit more below this, okay? But a perfect square is a number like 64 with a square root that's a whole number. That doesn't always happen where it's a whole number. A lot of times it ends up being a decimal, okay? So, let's list through our first 10 perfect squares. Let's list through our first 10 perfect squares. Seth?
There's always 1.
Okay, there's always 1. The square root of 1 is
1.
1. 1 times 1 is 1. So 1's a perfect square. Raise your hand if you know our next perfect square. Okay, Calsway? 4. The square root of 4 is what number? 2. Okay. What would our next perfect square be, Reese? 9. 9. Okay, we have the square root of 9, which is 3. Okay. What would our next perfect square be, Kelly? 16. The square root of 16 is what number, guys? 4. Okay, what do you notice about the numbers in the array? Are we just increasing by 1 every time? Okay. What's our next perfect square? Justin? 25, right? And that's funnier than 24 if we know SpongeBob. And the square root of 25 is 5. Okay? What? 27? From SpongeBob or from the perfect square?
No, it was like, yesterday someone was like saying 27.
That's weird. That's a weird flex.
Yeah, it was like 27. Yeah.
Weird. So what's our next perfect square after 25? Okay, Lucas. 36, right? Okay. The square root of 36 is 6. Okay. Then what comes next? Okay, Kelly? 49. The square root of 49 is 7, okay? Raise your hand for telling me what one's next.
Me.
Okay, Reese? 64. The square root of 64 is 8. I have a friend whose name is Nate, much like Nate here. But I always say instead of 8, I say Nate around him. So he's like really tall, so I joke with him that he's 8 feet tall. So then I joke with him that he's Nate feet tall. It sounds like 8. Or we play volleyball together, like just kind of randomly on Sundays. So we're probably gonna play this Sunday. And so whenever the score is something 8 or 8 something, I always say Nate instead of 8. But anyway, so Seth, get the next one.
I got the next 4.
Ooh, let's go to the next one though.
Number 2. 81 is
Okay.
9.
Okay. The square root of 81 is 9. Okay. And raise your hand if you want to give us our 10th one, which is what we're going to finish off with today. Okay. Seth, go ahead.
100.
100, right? You can even make it into that emoji if you want. Right? 100. Okay, guys, you can cringe. Yes, there you go. Good cringe. Okay. So you guys, okay, you guys have seen that before. Okay, let's look at the very back of our note packet. Woo! We're almost done with our first note packet in here.
Oh my god!
I don't know if anything's more lit than that. Okay? Hey, the real number system. The real number system. Wait, real numbers. Okay? I also heard you guys have filled out like basically this exact same thing before. That's dope. Okay? So that's what I heard is like
The
literally
exact same
that.
page.
So the real number system, okay? The real number system. Now you might be just looking at it like, does that mean there's a fake one? Kinda. We call it the imaginary numbers, but we actually don't get into that until algebra 2. But there is such a thing called imaginary numbers. We talk about it very, very briefly here. What was that? No, actually, infinity is not imaginary. But it is a concept. Yeah, it's a concept, not a number. No, pi is what we call an irrational number.
Google.
No. We'll talk about imaginary numbers very, very briefly later in this class. But for now, all we need to know is the real numbers. Okay, and that's any number you've seen before the real number. You've never seen an imaginary number before. Because they don't actually exist in real life at all. Okay. So we're gonna start most inside out. Okay. So if something's in this innermost category, that means it's also in the outermost, right? Okay. So our innermost, we have natural numbers. Natural numbers. These are the numbers you see just naturally in nature, okay? And then behind natural, we're going to put a capital N in parentheses. Because each of these number systems, there's different number systems inside the real number system. So there's a natural number system. It's just a set of numbers. Just a set of numbers, okay? And we can abbreviate that set of numbers with capital N. Now these are what we call counting numbers. We call these counting numbers. I'm going to do the number sign, apostrophe S for counting numbers. Okay? Not counting hashtags. Okay? Counting pounds. Counting octothorpes. You guys have probably not heard. Okay? It can also be called an octothorpe. Yes, it's a really weird flex, right? Okay. Counting numbers. Okay. So when you start counting, what number do you start counting with?
1.
1. So it's 1, 2, 3, dot, dot, dot. What's that dot, dot, dot mean?
Forever.
It keeps going forever, right? You keep counting forever. Okay? We start off with 1. What was that? Was that through a trillion? Quadrillion. Quintillion. Sextillion. Septillion. Or hectillion. Maybe septillion. But anyway, yeah. So then we have the whole numbers. Just outside of that, we have the whole numbers. So we have whole numbers, okay? And we'll abbreviate that with a capital W. Okay, that's a dub. Okay? So the whole numbers are all the natural numbers. It's all the natural numbers, all the counting numbers, and 0. So we just include 0 into it now. We call it whole numbers. So for examples, okay, for the examples for those, it'd be like 0, 1, 2, 3, dot, dot, dot.
Seniors, please report to the auditorium at this time. All
Let's see what's
seniors
written
to
on
the
that.
auditorium.
Let's see.
So we have our whole numbers, which are all the natural numbers, all of our counting numbers. We also add in 0. The 0 is not a counting number, right? You don't start off counting, well, how many desks do we have? 0, 1, 2. That'd be weird, okay? If somebody started doing that. Like you look at them like they have 3 heads, okay? So then right outside whole numbers, we have our integers. We have our integers. An integer, we actually don't use an I, we use a Z for it. We use a Z for integers.
What?
I'm not actually entirely sure why. I need to look that up. But yeah, I think it has something to do with probably the Latin word. But for integers, we use the capital letter Z to denote that. Now, integers are the whole numbers, so our 0, 1, 2, 3, so far on, and also negatives. So it's the whole numbers and it's the negatives of those whole numbers as well. So it's the whole numbers and it's the negative of those. So it's positive and negative whole numbers for the integers. So in this case, you could have like dot, 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 meaning it goes forever beforehand, like -2, -1, 0, 1, 2, dot, 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 okay? So not only do we have all the 0 and positive, we also have the negative whole numbers. No decimals or fractions, but we also have those negative whole numbers. Yes, Seth? Negative 0 doesn't exist at all. It's not even imaginary.
Why?
Yes. The 0 cannot be positive or negative. And it has no, as we call it, parity. 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 It's actually neither. Weird. It's kind of weird, right? Bless you and bless rain now after us. Yeah, it's kind of weird concept to think it can't be positive or negative. And then outside of integers, outside of all of this, we have rational numbers. We have rational numbers. And for the rational, we use letter Q.
Oh,
It's kind of weird, right?
that was just R.
Yeah. For real number system, we use R. So I know for that we had to come up with something different to use for the rational ones, because the real number system is R. Okay. So rational numbers are going to be all of these that come before it, but it's also going to include fractions, repeating decimals, decimals that repeat in a specific pattern, repeating decimals, and very good, terminating decimals. What's it mean to terminate?
It stops.
It stops. And terminating decimals. That terminator. You stop something, you eliminate something, okay? So you end something. So terminating decimals means it ends. So rational numbers, they include all the integers, but they also include any fractions, repeating decimals, or terminating decimals, okay? So some examples of these, okay, you could have like 5, just number 5. It's an integer, it's a whole number, it's a counting number, it's a natural number, so then it's also a rational number. 1/4, that's a fraction. 0.75, that's a decimal that ends, it terminates. 0.3 repeating, does that end?
No.
No, but does it? But it's repeating.
Yeah.
It repeats very specifically, 0.3333 forever.
0.123.
Yep, as long as you have the repeat. The square root of 4. Wait a second, what is the square root of 4? 2. And is 2 a natural number?
Yes.
So then it must be a rational number as well.
The square root of something.
Okay, that's very true. We'll talk about that one actually, a very specific example. Okay, so then, now notice, this one's a separate category. It's still in the real number system, but it's not a rational number, okay? It's not rational. Instead, we call it irrational. Irrational.
Pi.
And this is where we use our capital I. Oop, that was like a line through it instead of a line underlining it. This is where we use our capital I. Is the irrational numbers. So what does it mean to be irrational? The IR means it's
Can't put it into a fraction.
okay. That's true. Okay. So if it's irrational, that means that's an example. It's not rational. That prefix IR means not something. Okay. So it's not rational. Okay. It's like irreversible means it's not reversible. If you're irresponsible, it means you're not responsible. Okay. So irrational means it's not rational. So this is the category of numbers that are decimals that don't repeat or terminate, which we said means that they don't end at that point. So these are the decimals that don't repeat or terminate. They don't repeat repeat or terminate.
Hoping you would just say that one more time.
Repeat or terminate. So Seth was saying one earlier, and Elliot asked about this earlier, and the number pi, it's a symbol, but it represents a number. Pi, that does not terminate and it does not repeat. It goes on forever and ever and ever in a seemingly random pattern. 3.141592, blah, 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 blah. There's no repeat in there.
I looked up the 1 million numbers to pi.
Yeah. And it goes out forever. It goes out forever. It's crazy, okay? So then if pi is irrational, that means 2 times pi is irrational. If you double it, it doesn't mean it's just going to end out of nowhere. And if you double it, it's not going to make it end. It's still going to go on forever. It just changes what number the numbers are. Like if you have the square root of 4, which terminated because it's just 2. If you have the square root of 17, it doesn't terminate. So if I go over here and I grab one of my scientific calculators real quick, okay, and I type in the square root of 17 here, we're going to get a bunch of randomness, okay? It's not going to be a pattern. And even though, is it possible for the calculator to go on forever?
No,
No, why is that?
it hasn't stopped before.
It has a starting point. Like, the screen ends at some point, okay?
It's like really close.
So I type in the square root of 17, it ends up being 4.123105626. So it doesn't repeat, and it ends at some point on the calculator, and that's because it hits the screen. On the calculator now, we assume that if it goes all the way, bless you, bless your inside out, bless you, forget. We assume that if it goes all the way to the end of the screen, that it's just, that doesn't terminate, that it keeps going forever. Now, if it stops earlier, then we know it stops. Yeah, Cowsway. Pi over pi. What is pi divided by pi? What's anything
1.
divided by itself? 1. So that would end up being rational. What was that? So that would be rational, yeah. That's a good question. So Cowsway was like, hey, what about pi over pi? Well, anything divided by itself is always 1. Okay? So that would end up being a rational number. And it would end up being a natural number. It'd be a weird way to write it, but it'd be a natural number even. Okay? So the square root of 17 is a bunch of randomness that just keeps going forever. Another example is the square root of 7. That'd be the same way. Okay? And that's because these numbers are not perfect squares. These numbers are not perfect squares. So I was like, 4 was a perfect square, 9 was a perfect square, 16 was a perfect square, but 17 and 7 are not. You could also have 1.010010001000001 dot. Oh, binary. It's like a computer language.
That's code.
I hear what you're saying. So does this ever end? No.
Maybe.
And even though there's kind of a pattern, does anything repeat? No,
Yes,
it's not
the
the,
one.
it's not the same thing over and over again. Because here you have 1 0 then a 1, then you have 2 zeros and a 1, 3 zeros and a 1. So it's irrational because it doesn't just repeat. If it was 1.01010101 like forever, that would be rational because it repeats that. But this, it doesn't repeat it. Questions on that? Okay. So with this table, we're gonna go through this. We're gonna talk about what numbers, what number system, what number sets or set they would belong to. And we're gonna talk about why. So the fraction 1 over 6, is that a natural number?
No.
That's not a number we use to count, okay? Is it a whole number?
No.
No, it's a fraction. Is it an integer?
No.
No, it's positive, negative whole numbers. Is it rational?
Yes.
Yes. So if it's rational, could it possibly be irrational at the same time?
No.
No, it's one or the other. And then why is it a rational number but not like an integer?
Because it's not completely whole.
It's a fraction. That could be our justification. It's a fraction. Square root of 17, we said just a minute ago, it's what?
Irrational.
Irrational. So if it's irrational, could it possibly be any other category? No, okay. And so what I would write for our justification is we said it's not a what?
Perfect square.
Yeah, it's not a perfect square. Very good. Ooh, for example, here though, square root of 9. What number is that actually?
3.
3, okay? So where would that fall in line at?
All of them except for rational.
The first 4, because it was natural it's a counting number, it's automatically a whole integer and rational number as well. So if it's natural, it's automatically the next three. But we stop before we get to irrational. So we'll just go check happy, okay, and go through there. And our justification for that could be that square root of 9 is really equal to what number? 3. We know that 3 is a natural or a counting number. Okay, those are the numbers you see in nature, are those counting numbers. 0. What about 0?
Whole integer and rational.
Okay, whole, integer, and rational. Let's get in the habit of raising your hands on these, okay? So it's a whole, integer, and a rational number, okay? And so, we could say, our justification, you could just say 0 is a whole number. Or you could say 0 is not natural number, okay? You could say kind of either of those two things. There's probably some other things you could say as well. Negative 1.5. Negative 1.5. Raise your hand if you think you had this one. Okay, go ahead, Reese.
Integer and rational.
Okay. I'm going to disagree with integer, but it is rational, okay? Anybody tell me why it's not an integer? Okay? Lauren. It has a decimal. Integers, we won't have decimals on it, okay? It is negative, so we're like, oh, maybe that's an integer, but it has a decimal. And why is it not irrational then? Because it, Christian?
Because it's solvable.
Because it's solvable and it does it end?
No,
Does 1.5 end?
it is not.
It doesn't continue. Yeah, okay, gotcha. So it does not continue, it does end or terminate. Okay? So I'll say justification for that, it's a decimal that ends. You write terminate as well. It's a decimal that ends or terminates. So that's why it's not irrational. Well, we know it's a decimal, so it's not an integer. Okay, raise your hand for 3 times pi. 3 times pi. Okay, we had some examples like that earlier. Elliot.
Irrational.
Irrational, right? Okay. And our justification can be why. How do we know that?
Pi goes on forever.
Because pi goes on forever. Because pi itself is irrational. If pi is irrational, then 3 times pi will be irrational. It's not just going to make it rational. And raise your hand for the number 2. The number 2. Okay, Kelly? The first 4. It's a natural or counting number. That means it's automatically a whole number, integer, and rational as well. Okay? And our justification could be that this is a counting number. You use 2 when you count. Okay? Raise your hand for this bottom one. 1.12112, 1112, dot, dot, dot. Seth.
It's irrational because that's a pattern.
Irrational, right? No pattern, okay? So you can say there's no pattern. And it doesn't what?
Stop.
Yeah, it doesn't stop or it doesn't end. I would justify that. Okay, any questions or anybody still need this table? Questions on, or does anybody still need this table? Okay, you have something almost identical to this on your worksheet today. The only difference will be the numbers. Okay, so let's look right below this here at the bottom of the page. For each of the following statements, state if they are sometimes true, always true, or never true. So we're talking about different levels of truth, whether it's part of the time, all the time, or never. So whole numbers or integers? Raise your hand. Whole numbers or integers? Is that always, sometimes, or never true? Always, sometimes, or never true that whole numbers or integers. We could look up at a real number system there to help us out, Lucas. Sometimes, always, or never. It's always true. Whole numbers are always integers. Okay? Whole numbers are always integers. Okay? And how do we know that's true? All the time. How do we know that? Okay? Because it's positive and negatives. Okay? Because whole numbers are the positive versions of integers. Okay? Whole numbers are just positive integers. So you can say that, or you could say, so you can say whole numbers are positive integers, or you could say integers include whole numbers. We could say, it's in our chart, right? Integers include whole numbers, to explain that. Okay. Integers are whole numbers. Is that always, sometimes, or never true? That integers are whole numbers. Talking about whole numbers being integers, is it always true the other way around? Seth, what do you think?
Sometimes true.
Sometimes true, right?
0.
It's it's sometimes true. 0 is a whole number. Okay, so only what kind of integers are whole numbers? Kelly? Exactly. Only positive integers and 0. That's our explanation. Only positive integers and 0 are those whole numbers. Okay. If a number is an integer, then it's also a rational number. So a number is an integer, and it's also a rational number automatically.
Yes.
That's sometimes, always, or never true. Sometimes, always, or never true. Kelly? That's always true, right? Always true. Okay? And we know that because all integers are rational. All integers are rational. The number 5 pi is a rational number. Is that always, never, or sometimes true, Nate? Never true. And why is that? Very good, because pi is irrational. A number can be both rational and irrational. A number can be both rational and irrational. Ben?
Never true, because if it's irrational, then it can't be irrational.
Very good. Never true, okay? It can only be one or the other. Because if it's one, then it's automatically not the other. Just like if somebody's responsible, they're not also irresponsible. They're one or the other. If a number is rational, then it is also an integer. If a number is rational, then it's also an integer. Sometimes, always, or never true on that. Reese? Sometimes. Sometimes. Okay? Can you have decimals in an integer? No, so no decimals. And I heard also no fractions. No decimals or fractions. No decimals or fractions there. Okay, then we have our last one here. Rational numbers and irrational numbers are real numbers. Rational numbers and irrational numbers are both real numbers. Always, sometimes, or never true. Whitney, what do you think? Okay, let's look back at our chart. So where's the real number system? Is that all of it or just part of this? Always. Okay, so it's always true. Because all of these categories we learned today, all categories above are real numbers. All categories above are real numbers. Okay, questions on that at all? Okay, so those last two things we just did, the table and these always, sometimes, never true, that's basically your homework assignment is, okay? I'm going to pass that here in a second, okay? And we'll have the remaining about 10 minutes here to work on that, okay? You guys can feel free to pop in music during that. That's perfectly fine by me. Just don't let your phone or laptop be a distraction to you in that if you're putting music in. Just go ahead and select your music. Don't take a ton of time to do that. You're really just taking away from work time here, okay? You guys can get a great head start on this, okay? You get a great head start on this. And even potentially finish it and have no homework, okay? That'd be nice to be able to finish that as well, okay? If you have any questions, as always, please ask. Okay? I would like to ask. I want to help you guys. But unfortunately, I'm not a mind reader.
How cool would it be to work?
Right? Only if I could choose to read mine on laptop. Because I wouldn't want to just always have to read minds. Because, like, to always know someone else's thoughts, yeah, that'd be creepy. Yeah, if you, like, always heard out someone else's